A big thank you to the Talk Python team who sponsor this episode of the podcast. If you want to get better at Python, now is an excellent time to take an online course. Whether you are just learning Python to delve into great topics like artificial intelligence, or you need to go deep into things like APIs and async, my friends at Talk Python Training have a top-notch course for you. Visit talkpython.fm/mind to find your next level and get a 10% discount. Also a big thank you to all my Patreons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience and other interesting topics to educate, inspire and engineer people's minds all around the world. I'm your host Joseph, and for this episode of the podcast I'm very happy to have Paul Azunre on my show. He is the author of the great book called Transfer Learning for Natural Language Processing. Paul holds a Ph.D. in computer science from Massachusetts Institute of Technology. In his dissertation he developed novel global optimization techniques for previously unaddressed problem classes, including parabolic partial differential equations, to improve the optical efficiency of solar energy. He has served as a principal investigator on several DARPA research program teams, advancing the state of the field of natural language processing, short NLP. He has held the role of research director in artificial intelligence, machine learning, data science, and NLP at companies ranging from small, rapidly growing startups such as New Knowledge, Yonder, to large companies such as Dun Bradstreet. His work has been published in major peer-reviewed international research journals, and he frequently contributes as a program committee member at top conferences in the field. He founded the startup venture Algorine, a research lab spun out of the MIT to advance basic AI, ML, and optimization research, and seek high social impact applications. And now, ladies and gentlemen, here is my conversation with Paul Azunre. So hi Paul, welcome to my podcast. It's really a pleasure to have you here. And what we'll start with is give us like a 1-minute bio about yourself, what you do, what you did in the past, just to give the audience an overview of who you are.
Hello, Yusuf. Very nice to be here. My name is Paul Azunre. I am an NLP researcher. I did my dissertation work, my Ph.D. work at MIT in optimization, mathematical optimization. I was applying it to solar energy. This led me down the path of this computational path, which is optimization. It's kind of similar to machine learning. And so at some point I switched to machine learning, particularly in the context of fake news detection at a company called New Knowledge, which is now called Yonder. We were one of the companies that was battling, this scourge of, influence operations that has becoming more, prominent over the past few years. And that's how I got involved in NLP. And now I work in NLP proper, and particularly I'm studying transfer learning for NLP.
Sounds super interesting. Can you maybe, for someone who is not familiar with NLP, explain what NLP is, what it stands for?
NLP stands for Natural Language Processing. Thank you for that. And natural language processing is just a name given to the set of methods that we would use to train a computer to understand human language. Understand human language, make decisions on it. Mm-hmm. And this is, of course, becoming more important today because, we have the internet, we have all this data that human beings can't possibly read, all of it. So we actually need machines to read the data at scale to, for instance, detect cybersecurity threats. An example of those could be an influence operation in somebody's democracy, right? Mm-hmm. Or many other examples, like people breaking into, analyzing signals, speech signals to see if people are, terrorists trying, maybe organizing for some cause, right? These are all things where NLP could be used. Of course, things like medical diagnosis, from, reading data about a person, right? These are all places where natural language processing has become very important.
Mm-hmm. Got it. Can you explain us why NLP is, in its sense, so easy? So the concept is quite easy, but we cannot hard code everything. So why is it still so complex to get NLP right?
Think a lot of methods for NLP really matured over the past couple of years. And when I say methods, I mean in particular this transfer learning idea, right? So before, the current ongoing revolution, we definitely had a lot of tools that worked okay, but there were some deficiencies in them, or there have been deficiencies in them. Like one example being that, we were training systems from scratch a lot of the time, right? So human beings, if you think about the way human beings learn, we do not learn things from scratch every single time, right? We make associations with what we know and we build on that. But for a lot of NLP systems until recently, that wasn't truly the case. There have been, this idea is not, I should say, not new, because transfer learning, like if you use word2vec, you are already doing transfer learning, right? Because somebody pre-trained the model, you took it, and now you're repurposing it. But those classes of methods had a lot of deficiencies. Deficiencies such as, the word level, and so they couldn't, they were very brittle. If there was a word out of vocabulary, right, they would break. Like that makes a system very brittle, right? You want a system to be stable, right? Because somebody may misspell something on social media. Actually, people do all the time, and actually on purpose, right? So a system that doesn't take that into account can't work. And so progressively over the past few years, a couple years, it's really accelerated. We've been overcoming those hurdles faster and faster. And so actually now NLP is surprisingly effective if, you have access to the right set of methods, which are all open source. So,
yeah. Can you talk about this specific moment, this ImageNet moment of NLP, and when it was and how you felt about it, or how do you feel about that?
Okay, that's a good one. This one comes up a lot. So maybe it's very important first to talk about the original NLP moment, right? Which happened in, the original ImageNet moment, which happened in computer vision. So if you think about the way today, if someone is going to build a pizza, not pizza classifier, they're not going to train a model from scratch. But a model is huge, but you can train it on your GPU in probably an hour and have a decent classifier. And the ImageNet moment was when that became possible. And so before that, we had a lot of the components, but people were training their systems from scratch. So you needed to be, say, at a big research lab, MIT, Stanford, or whatever the big internet company of the day was, in order to train an image classifier, right? But what happened is that, first of all, we created a data set called ImageNet, surprisingly, which had good coverage and had in it enough general elements such that when you train the system on it, that knowledge could transfer to basically everything. And the reason that worked was because ImageNet has in it about 1,000 classes of objects, right, that were picked in a way that, covers the kind of things that a computer might see, right? And so that availability of that data, when we combine that with the availability of computing power, and the GPUs, through the GPUs in the personal gaming market, so all the elements were right and basically exploded. Now all of a sudden, and combined with a set of methods for fine-tuning the model. When I say fine-tuning, it means training a very small subset of it, right? So if you think about, so today, because of that moment that happened, it's been a while, it's very pretty standard in computer vision now, to download the model and only fine-tune a small subset of it, right? So we have the methods, we have the data, we have the computing power, right? Until recently in NLP systems, that wasn't the case. Like people, you need a lot of labeled data, which takes a lot of efforts for any particular task, right? And then it's expensive, and so people don't want to deal with it. But now, there have been particular innovations in NLP. One of them being the way we self-supervise the system, by which I mean, like the models that we are talking about today, all of them are trained with a target which is very easy to generate, and you don't need humans to generate it. The target, by the target I mean next word in a sequence, right? If a sequence of words is coming in, what's the next word, right? You don't need a human to create the data for that. That's just self-supervised. You throw the data at the model, and it looks, it has the sequence, so you can drop one of the words and try to predict it, right? That's very easy to do. If-then statement, right? And actually, that idea has now become, so it started with the predicting the next word in a sequence. Now it's more like fill in the blanks. So now we drop a few words, and then we try to predict the words in it, the way we dropped. And then we also try to predict maybe the next sentence. So there are variations of this idea. But all of this stuff does not require manual labels, which means we can train the model, and we have so much data, we can just throw it at the model. So basically, all of this, most of these models were trained on basically, the internet, right? Like all the books, all the books we have digitized, and Wikipedia, like everything, you can just throw at it. And then also computational innovations. So of course, when you try to train on that, so much data that's a lot of computation, right? But so some techniques like the transformer have made it easier to scale that to a lot of GPUs. So Google can now train it very fast in their GPU farm. Additionally, we've come up with methods for fine-tuning. Remember how in the original ImageNet moment we were saying we would tune only maybe the last 2 layers of the pizza, not pizza. Right now, we've come with a very similar set of methods for fine-tuning maybe a couple layers of the language model. Actually gets more sophisticated than that. Some people have found that if you vary, say, the learning rate in a certain way, or if you unfreeze the model gradually, those sorts of things, it can make it easier to like not overfit and all of that. So this set of methods are basically equivalent to retraining those last 2 layers of the computer vision system. So now we have all the elements, right? We have the cheap labels, we have the computing power, and we have the techniques for training it quickly and also adapt it locally very fast. So all the elements, and of course, takes off.
Got it. Can you talk about the major technologies today? Like, which are the strongest models you know about today?
Oh, it changes every day. But very, very, very quickly. I would say today, Albert is the strongest model, because if you look at the GLUE leaderboard, GLUE stands for General Language Understanding, I think, evaluation, and it's basically a set of tasks very similar to ImageNet in that it covers the kind of things you might want to do. So it covers things like question answering, and parts of speech tagging and named entity recognition and all of those things. It's a general set of tasks. So people evaluate their models on that, and there's a leaderboard, which at any point in time you can look at, and it changes a lot. So it started, the ImageNet NLP moment started with Elmo, I would say. It was on top, and it was using recurrent neural networks. And then BERT knocked it off. BERT uses, instead of the recurrent neural networks, it uses transformers. And so it could be a bigger model, and so knocked off Elmo from the top. Now people are beginning to realize that, some people are still building bigger and bigger models. I think last week OpenGPT-3 was released,
exactly,
right?
Yeah.
The biggest one. It's ridiculous. But even the authors of that paper said, we think this is not the right thing to be doing. And so actually, the field actually realized some time ago that maybe we should be making the huge models we already have more efficient, right? Ooh, imagine that. And so right now we have things like Albert, which is a modification of of BERT, which has done some innovations on how to reduce the number of parameters without, sacrificing too much performance. And this enables BERT to become, 90% smaller. So we are talking about 120 million parameters becoming 12 million parameters, right? So it becomes even easier for people to just start doing this stuff everywhere, right? So Albert, if you look at the chart, Albert is at the top. However, this question, right, has to be answered in the context of the particular application and all the other constraints of an engineering project. And it might not be the model. I just have to say, it might not be the model you choose just because, dependencies, right? You may actually, or the problem can be solved with the simplest thing, like a keyword match. If the problem is really structured, then there's no need for it. But if you are looking at the hardest perception problems, like translation and natural, like really understanding the language, probably Albert will be your choice. But there are other things like distilled BERT is another, there's something called prune BERT now. So more effective variations of BERT, and they're probably going to be, it's going to be another one tomorrow. So keep watching the chart.
Yeah, I see. Super interesting. Talking about these models and these billions of parameters they sometimes have, where do you see NLP going into the future? Also considering, for instance, mobile development. Is this something you are very curious about and very happy about, that this will be more common in the future? Where do you see the future of NLP going?
The future of NLP is definitely going towards more efficient variants of these transformer-based models. That's what I see. There's a lot of activity there, and it makes sense. And actually, it makes mobile development easier, right? Because now you can do all of these things on a mobile phone, which is ridiculous. And of course, the applications, I think there's a lot of exciting applications just because the opportunities have opened up, all right? So most of the world's languages have not been translated, for instance. Some are, disappearing, and before, like, in some countries, perhaps, or for somebody in a certain economic situation, they couldn't, say, get, 10 GPUs on EC2 to train a model for 2 weeks, right? That's not economically feasible for them, right? But they have problems, like maybe medical problems they could be solving in their community, right? But they couldn't, right? Because the barrier was too high. Now all of a sudden they can. Like if they have a laptop with the modest GPU on it, they can do this. So I think there's almost like a wildfire of applications. The possibilities are endless. I think we definitely need to understand what the models are doing best. So machine learning, I think, as a field, is very experimental, and of course that's driven by just the nature of everything. It's like the models are huge. You can't, prove theorems about every single part of it. It's just so complex, right? But there is definitely a recognition that we need to understand them more. So theoretically, there's a lot of work ongoing that tries to explain how some of these models work and how, alternative explanations and, because that will drive the research on what's more efficient. But yeah, just to TLDR, more efficient variants of transformer-based models, right now, that's definitely the trend.
Mm-hmm. If someone doesn't understand what transformer-based models are, what is the main idea, maybe in 1 or 2 sentences, if it's possible to explain it in a very simple manner?
Yes, actually it can. And maybe before I explain it, maybe I make an example.
Mm-hmm.
So let's say you had a sentence like, the prison inmates was speaking on the cell phone from inside his cell to his friend about cell biology, right?
Yeah.
Because maybe he knows something about cell biology. So when a model looks at each one of these words, how does it know which meaning it is, right? So, like a model like word to vec can't really do that. Like, I mean, it takes it it gives you the meaning that's the average meaning of all the words that all the ways it's being used in it when it was trained, right? But so you can't disambiguate, and the transformer achieves disambiguation. And basically, the way it does that is by looking around the word to see what the context is and make the decision based on the context, right?
Mm-hmm.
So I'm using a lot more than one or two sentences, but I hope it's very simple to understand. So you just look around. Or another example, like a word like he saw the duck, and so he ducked, right? One is a verb, the other is a noun, right? So if the model could look around to see that, oh, okay, this is a verb, this is a noun, then you could assign the meaning accordingly, right? The transformer basically achieves that, and it does that using something called a self-attention.
Got
Okay,
it.
so just look around to determine the context.
Mm-hmm.
Yeah.
Got it. Now another question. You are originally from Ghana, and I'm not sure if there's a Google Translate available or not, because you have a special language there. How is it? How can models like you're working on in NLP, how can it help countries like, for instance, Ghana and other developing countries, I would say, to improve in life? What would you say? It's a more maybe philosophical, economical question, but maybe
No, you're hitting the nail right on the head. So in Ghana, actually, we don't have just one language. We actually have
multiple.
a lot of them,
Mm-hmm.
and none of them have any translation technology, which makes a lot of things difficult, right? Where transfer learning for NLP can help with translation in particular, in those kinds of languages. The challenge is data. So there's a lot of data for English, Russian, Chinese.
Mm-hmm.
There isn't that much, and these models are data hungry. You need that's where the revolution is coming from. There's so much data that you can just learn everything. But there's not so much data for these languages in Ghana. So what do you do? Well, transfer learning can help there. And actually, there's a variant of BERT. It's an example I used to explain this. It's called multilingual BERT, that was trained on over 100 languages. None of them includes any Ghanaian languages, but in the same way we were training on ImageNet on a general data set, this is kind of like been trained on a general data set of languages. So it's learning the commonalities between many languages, right? And so there's definitely learning something that might transfer to other languages, right? And so you can use this transfer learning idea to initialize multilingual BERT to whatever language you're trying to those parameters, and then fine tuning it on the data that you have. You still need a sufficient some amount, but there are sources you can find. There's a Jehovah's Witness data set that has translated basically literally all the languages to some high resource language, right? So you just need an unsupervised part anyway. You just need a corpus in that language. There are sources that release texts, like the Bible has been translated to everything. And of course, you don't want your model to be, at the end of the day, represent about the Bible. It has to be about human life in general. But again, you initialize somewhere, you move the model closer to where you want it to be by feeding it maybe the Bible, and then you start adding the real data, right, that you are able to collect. And because you've gone through this process, you don't need billions of words. You may get away with, depending on the stage, less and less, right? So I'm the founder of an organization called Ghana NLP that was formed with a couple colleagues to basically address this problem. And these are some of the things we are doing. I trained the language model to be predicting words, filling in the blanks, kind of smart compose for our language tree. And so now I'm able to do all of this, combining it with some of the, efficiency improvements we talked about earlier. I'm able to train this model in like 15 hours. It's ridiculous. And it's filling in the blanks. And I haven't fully transferred it to like the real colloquial speech. This was trained on Jehovah's Witness data, but it's filling in the blanks almost perfectly now. And that was 15 hours on one GPU. It's becoming extremely accessible to do this, right? So it's very exciting to me. And this touches anything. Once you have a language model for the language, you can do cybersecurity, right, online, for instance. Right? A lot better than you could before. You can classify things into positive and negative reviews if that's what you're trying to do, or classify patients into urgent care or not urgent care. There's just anywhere you look, right? There is an application. So I'm very excited about it. I think anyone who understands it's extremely, and there are a lot of people. I've not seen like a technological revolution like this before. This is the most, if you just follow the people, in the field on Twitter, the kind of things you see happening every day, like literally every day, it's shocking. And all of it kind of derives from this concept we described various, innovations in there, but it's just breakneck speed, breakneck speed. So I really hope anyone watching this checks this out. There's an opportunity to do something very remarkable for everyone,
Absolutely. That's good that you
There's
say
definitely
it.
no shortage of problems.
Yeah, absolutely. It's so cool that you said that, because I wanted to talk about how people can dive into this field. And you wrote a book called Transfer Learning in NLP. And can you maybe talk about it? How is it structured, and what can people expect from your book?
Okay. The book is written to be an introduction to the topic. So we try to keep things extremely accessible. One of the challenges of the field is because it moves so quickly. There's no standardized material. A lot of people are doing, very good work, excellent work, and I learn from it. And I follow them on Twitter and I talk to them all the time. But in my experience, it's been extremely inaccessible. You can find blog posts. You can read the papers if you have that skill, but that's not the skill everyone has. You can read the blog posts, and there are a lot of good ones, a lot of good blogs, but kind of scattered all over the place. So to find the story, the most essential parts of the story, up to a certain, like very quickly, so that you can start solving your own problems, it has been somewhat challenging. So this is what the book tries to achieve. It goes through, first introduces you to this historical context of where we are, where we came from with all these ImageNet things, and then starts introducing you to the key architectures. It provides the code. So the code is free. It comes along with the book. We hosted it on Kaggle. And so within a couple minutes, you can hit copy and edit and start running the thing. And Kaggle offers you 30 hours of free GPU time per week. I've not needed more than that in writing this, so it should be sufficient for you to run it. So you will get this free GPU. You can use Colab Notebook if you want, but we recommend Kaggle just because everything's set up and attached, and you can just hit run. And so within very quickly, the hope is very quickly you can copy the code and just change it and apply it to a different problem, within hours. That's our hope. So very accessible, and hopefully after you read the book and you start solving your own problems, you go and follow a bunch of sources that you like, and then of course keep your eye on the field because it moves very quickly. But this will bring you to a point where very quickly you should begin to understand what's going on.
That's incredibly cool. I will put a link of the book from Manning down in the description if anyone is interested, and I'll also provide you with a discount code so you can save some bucks when getting the book from Paul for sure. Is there anything else, maybe some motivating words at the end you want to give the audience, Paul?
Yes. I think it's important to democratize the ongoing technological revolution in NLP, not just in NLP, but overall. And specifically in NLP, that's what I can do something about. I think a lot of cultures can be left behind, like our rich cultural heritage as humanity can be lost, and also a lot of human suffering could be solved relatively quickly if we just made these benefits accessible to everyone. So, and I hope that transfer learning and NLP is one way that we can achieve that, and I hope it interests you. But there are lots of different other ways to achieve that. For instance, ethical AI, understanding, when you're sampling data and you're making sensitive decisions, be sure to think about, how you sample so that it's not biased in some way, those sorts of things. As I think we've not been thinking enough about the ethics of what we are doing. A lot of things have been driven, by economics purely, and it has improved human life dramatically. And so we are all very grateful for it. But we also need to think, now we are at a place where we should spend more time thinking about the ethics of what we are doing and about democratizing what we are doing, because this helps all of us, So.
Absolutely. These are very motivating words, Paul. I would say thank you so much, by the way, for compressing your huge amount of knowledge into this short podcast, though. And I think people listening to it will learn a lot from NLP. And if they are interested, they can, of course, get your book or delve into the field of NLP by reading blogs, following you on Twitter and so on, or other people on Twitter as well. With that being said, thank you so much for your time, Paul. And I'm looking forward to hearing from you maybe in the second part, let's see, in the future.
It's been nice to be here, Yusuf.
Thank you so much. Bye-bye.
Have a good day, everyone.
You too.
Yeah.